Let's cover how we can have a state determine when it should exit or not. Normally, transitions have that logic defined in there, but it can be beneficial at times to let the state determine this. So to show this, let's just do something stupid simple. Let's have it where whenever your character jumps, it will increment a counter, and it will determine what state you're in based on the number of jumps you have executed. Let's start by creating a node class. Let's also get a transition class. And with the node class, we'll start off with the number of required jumps. Make it visible. We need to detect when the character jumps, and we're using a third-person character. So under input action jump, we're going to call a new dispatcher. And I mean, while we're using jump to demonstrate this, like this could be like an item pickup, or like an objective complete, and then we'd have our own event for that. Back in the jump state, we're going to want to grab our context. We'll bind an event to when the character jumps. And we'll want to clean this up on state end. Let's create our own variable to track how many times he has currently jumped for this state. And we don't want to make him visible because this is just for internal tracking. And every time you jump, it will increment. Create the state machine so we know what we're going to be working with. When using state-driven transitions, there are two different approaches you can take. One is you can have the transition look behind and determine if you should move forward or not, or we can have it look ahead to determine the criteria. For the first approach, let's look behind. It's a little bit simpler. And what that means, though, is you're going to move to the state first, and it won't exit until the criteria is met. So in this case, at 0 jumps, it should exit right away. And then once we reach this state, it will stay in here until you've at least jumped once. Open the transition class and override canEnterTransition. We're going to grab the previous state instance, cast a jump state, and then verify that the number of jumps is equal to the number of required jumps. Back under the state machine, make sure to set your transition class. And let's add another state. Open a third-person character and add in a new state machine component. Set this to the state machine we just created earlier. Start it on begin play. Let's play the state machine. It starts off going immediately from the first to the second state, which we expected. If we jump once in here, it switches to the next one. We have to jump twice once we enter this state because the counter is per state. We would have to store the counter somewhere else, like on the blueprint itself or the context, if we wanted to make those numbers total values and not reset per state. Let's go ahead and set this up so it is a look ahead method to determine whether the transition should continue or not. Now, it's a little bit interesting because the previous state is what's tracking your current jumps. And the required jumps in this case will be in the next state. So we can do a couple things. We could move the required jump, or the number of jumps, off of the state and move it to the context or on the blueprint itself. And that definitely works. But to show you both, in this case, a method that looks back and forward, let's just leave it like this. And so all we're going to end up doing then is changing the jump transition. So this is where it'll be a little fun, is the previous state, we're going to leave that to get the number of current jumps. And we're also going to get the next state to get the number of, or to get the required jumps. And for this example, we're just going to assume that the casts are always correct, which they really should be. There's one more thing we need to do in the case of a look ahead, and that's we need to evaluate the graph properties of the future state. And this is important if you have an actual variable in there. In our case, we just have default values like the number 1 or 4, and so it doesn't really matter. But if you have like a variable there, we have to call this, otherwise it won't be evaluated until the state is entered. And so just make sure to do that. It's only necessary on future states. The past state will always have had its graph properties evaluated by that point. So back in the FSM, we have to look at this a little bit differently. In this case, because this is the initial state, we will still enter this first. However, it will stay here until you jump once. And then it'll stay in this state until you jump twice, and then 4 times again in the final state. Once, 2. I just pressed spacebar 4 times there to speed it up. Say you want to have a state end from an event-based approach, but you don't really care about any other requirements than firing an event. Now you can do that too. Let's create a couple of new node classes to demonstrate. In the event state, we'll create a new dispatcher. And just to show it off, we're going to just do a normal delay node of 1 second. And then we'll say it should end. This is something you could also do like under the state update. Pretty much whenever you want a state to end, you should call this, but you should call it after all their logic is finished. And you should not call it on event state end, because this right here is what gets called once the state is officially ended. So at this point, it's too late to do anything. And the reason you want to call this at the end of your execution logic is because what will happen is anything past this point will still continue to execute, even though the state is ending. And you should just avoid that for just as a good design. Make sure to compile, otherwise the delegate won't be created properly for the state machine to bind to. And let's create our new state machine. Add event state, add a regular state. And for the transition, we create our own class for it, but we actually don't need to use that unless we want to set up manual binding for reusability. Another way is we could set the delegate owner instance to previous state and then set the delegate to what we just created. Under third person character, let's go ahead and change our state machine to use the new event SM. And you saw after 1 second, it switched to the next state. So it is working as intended. Now, if you want to switch between multiple different states, you would need a delegate for basically every state you want to switch to so the transition can bind to it, or you could create a delegate that has like a parameter and then have the transitions listen for that. Let's try to come up with a way that lets you choose which state you want to switch to using one delegate in a way that's reusable for multiple state machines. So let's create an event dispatcher on the state machine level. Switch to state. And let's give it a state name parameter. Let's open up the event transition class that we never ended up using. Override on transition initialized. And get the state machine instance this is part of. This is the blueprint. Cast to event SM. Find event to switch state. Now let's get the next state. And we want to do a comparison of the state name and if this is true, we want to set that this is possible to evaluate. Make sure that we set candidate value to false on initialize. And then clean up at the end. And the last thing we have to do is under can entry transition, make sure it's set to always true. Back under the event SM, let's go ahead and delete all this for now. We'll just create a normal state to test this out. And then another state after that, and the transition for this will be the event transition. We'll just do a delay node once again. And we want to switch to the next state, which is, in this case, state 1. Let's call it something else. And after 2 seconds, it switches to the next state. And that is a way to dynamically switch between multiple states without having to define individual transition logic. You can also put that in the state class as well. So instead of having this should state end, we could get the state machine instance. And here, I mean, you're going to want to probably make child classes of this or use a variable for this since we have to know the name specifically. But this has the same impact as before. The last thing I want to go over is it might get kind of tiresome to always set the transition class, especially if you're going to be using this approach frequently. So what you can do is under the event transition or whatever class you're using, under class defaults, behavior allowed connections, we can specify a rule that will always place this transition whenever it's connected. So if we add a new connection, there's a from state option. And for from state, let's just use event state. And we'll leave these set at none, meaning it doesn't matter what state it's going to, and doesn't matter what state machine class it's in. All it cares about is if you're connecting from an event state. And so back in this, if we drag well, those aren't event states. This is. So if we drag out from here and just add in another event state, you can see the connection is automatically solid because it applied the event transition class automatically. This is a normal state, and so if we add a state from here, it doesn't apply it. But if we add another state from here, it does, since this is an event state. And so that can just save you time if you want to take this approach. And you can use these rules for any other scenario also. So hopefully this helped cover a few different ways you can use states to drive transitions. It can be very useful when you can define the rules directly on the node itself. It's still recommended to let transitions decide when a state should end or not in the majority of cases. Logic Driver is designed to follow a traditional FSM approach, and states are basically determined by the transitions. That's why Logic Driver has the logic within transitions themselves. But hopefully this helps you. Please let me know if you have any questions.